Hello everyone, this video is brought to you by the Atılım Üniversitesi OpenCourseware project for the course Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak and video lectures are prepared by Ümit Alkuş. In this video, we will solve one problem in Chapter 11. A merry-go-round of radius 3 meters is rotating at 8 revolutions per minute about a frictionless vertical axle. A 30 kg duck jumps onto the merry-go-round and stays on the edge. If the moment of inertia of the merry-go-round is 325 kg times meter squared, calculate the final angular speed of the merry-go-round in revolutions per minute. First of all, we write the given quantities in SI units. However, omega 1 has units of revolutions per minute, which is a non-SI unit. We leave it so, since we will calculate the final angular speed of the merry-go-round in revolutions per minute. Because the net torque on the merry-go-round is 0, then the angular momentum of the system is conserved. Namely, tau equals dl over dt equals 0 if and only if L is constant. Therefore, L1 equals L2, where L1 is the initial angular momentum and L2 is the final angular momentum. Since L1 and L2 are equal vectors, their magnitudes are also equal. Then we write L1 equals L2, and by the expression for angular momentum we write I1 times omega 1 equals I2 times omega 2, where I1 is the initial rotational inertia of the merry-go-round and I2 is the moment of inertia of the total system, that is merry-go-round plus duck system. Namely, I2 equals Im, which is the rotational inertia of the merry-go-round, plus I-duck, which is the rotational inertia of the duck after it jumps onto the merry-go-round. Then it is equal to m times r squared. Now, if we put this value into the equation, we obtain I1 times omega 1 equals Im plus m times r squared times omega 2. Since I1 is Im, that is the rotational inertia of the merry-go-round, therefore we find an expression for the final angular speed as omega 2 equals Im times omega 1 over Im plus m times r squared. Now we insert the numerical figures into this equation. Then we finally calculate the final angular speed as approximately 4.37 revolutions per minute. Alright, this brings us to the end of the discussion of this problem. Thank you for your attention and see you in the next video.